Hello, welcome to episode 2C. Before I actually do an example, I want to talk about IVPs, or initial value problems, with the conjugate pairs. So, the first thing we're going to do, we're going to have this initial value problem. So, what do we want to do? Well, we want to solve this first. So, we're going to do our characteristic polynomial, ar squared br plus c equals 0. And we go ahead, we chug through the quadratic formula, and I'm not going to be doing that, but I'm not going to be filling these values in because we're trying to be somewhat general here. So, and then we're going to say that this is equal to, okay, some alpha plus or minus I of beta. Okay, great. So we get our solution. Y is equal to e to the alpha t times c1 cosine beta t plus c2 sine beta t. Right, and that's it, all said and done. But now you need to consider this an initial value problem. So we need to take our prime and we need to basically substitute y of 0, and we need to take the derivative. So we have to find what y prime is, right? And if you notice, we have three functions, and these are both three nonlinear functions of t, right? So it's going to, okay, so we got to do e alpha t, and okay, that's going to be the same stuff here, plus e alpha t, and then, okay, minus c1 beta sine beta t, right? And so this kind of gets a bit annoying to do, but there's some sort of shortcuts that I'm going to show you here for solving this. So the first one to notice is that y of 0 is going to be e to the alpha 0, c1 cosine of 0 sine of 0 c2, right? So what does that tell us? Okay, so first of all, we have three functions. E to the alpha of 0 is 1, cosine 0 is 1, and then sine of 0 is, well, 0. So what does that tell us? Well, y of 0 is just c1, right? It's just the cosines, the coefficient of cosine. So we can basically, okay, and that's equal to lambda. So we can easily, we don't need to actually do much for that. We basically get lambda for free. Now, y prime of 0 is equal to this, what is that one? That's eta. So, okay, but now we have to take the derivative. But first of all, let's think about this for a second. The derivative of cosine is going to be sine, and we know that sine of 0 is 0. So we don't even have to take the derivative of this cosine. And this e to the alpha term, well, it's going to be the same on both sides, right? And actually, I forgot that we need an alpha term here, right? It's going to be the same on both sides. So we can pop this e to the alpha out once we differentiate. So we don't even have to think about differentiating that, right? So when we expand this, it's going to be alpha cosine of c1 cosine beta t, and then sine, or c2 sine beta t. That's good. But okay, so that's well and good and all, but one thing we know that this is 0, right, at t equals 0, so we can cancel that out, and here we are just left with alpha c1, right? So, and then once we differentiate, well, this is going to be 0, and then we're going to get this plus c2 cosine term, right? So we can pretty much cheat a little bit, because with this y prime, the only y prime we're essentially interested in is going to be, you can get this sort of y prime with this bar over it. It's going to be alpha c1 plus c2, right? So actually this is, it's better I just actually write explicitly what that is, and that is going to be eta. right? So eta is just alpha c1 plus c2, right? So we don't even have to take these full derivatives. We can just use the fact that these have some cyclical patterns. And then obviously if we had maybe, actually I'll talk about what happens if we happen to have a y triple prime here when I talk about higher order differential equations, but it's pretty much the same process. You can cheat a little bit with that. So what ends up happening here, okay, so C2 is just equal to, and obviously this is lambda, so this becomes eta minus alpha lambda. So what is y is equal to e to the alpha t times lambda cosine beta t plus eta minus alpha times lambda of sine beta t. Alright, and so hopefully this helps you out in solving problems. In the next step, we're going to look at solving a problem. See you then.